6 is finishing up, finishing with sequences. And probably the main thing in this section is this thing called the monotone convergence theorem. Okay, the monotone convergence theorem. Okay, so let me just sort of review what this was about. Who can tell me? Can anyone tell me what this is about? I don't know. Can anyone give me a sense of what the monotone convergence theorem is about? What's a monotone sequence, for example? What's a monotone sequence? Yeah, Rachel.
It's a sequence that's either always increasing or always decreasing.
Right. Okay, so remember last time we defined these things called increasing sequences and decreasing sequences. Right, and we said that an increasing sequence could be something like this. Just to remind you, it could be something like this. The way we distinguish between that and something which has to be constantly increasing is by the word strictly. So if we say strictly increasing, then this is not strictly increasing, right? This is not strictly increasing. It goes flat at some point. Okay. So if I say strictly increasing, I mean it will be something like this, right? The values are always strictly bigger than the previous values. Okay. And similarly, we have decreasing sequences and strictly decreasing sequences, and all of these guys fall into the category of all of these things are so-called monotonic or monotone sequences, right? Right. They're monotonous, right? They don't vary that much. Okay, and then we have this thing called the monotone convergence theorem, which tells you about the as you can see from the name, it tells you about the convergence of monotone sequences, right? So monotone convergence theorem. Okay, can anyone tell me what that's a Taylor? Yeah.
If it's monotonic and it is bounded,
yes,
then it has a limit.
That's right. So if so it goes like this. Say a sequence is monotonic. Okay, so it's either strictly increasing or increasing, or it's strictly decreasing or it's decreasing. Okay, suppose the sequence is monotonic. Then the sequence converges if and only if the sequence is bounded. Okay, that is, convergence and boundedness turn out to be equivalent conditions. If you have a monotonic sequence and you can show that it's bounded, then you know it's going to converge. Okay, so for example, right, if I look at the numbers that the square root of 2, right? The square root of 2 is something like 1.4142, something. Right. If I look at those numbers and I make them into a sequence as follows, I say I'll let the first guy be 1, the second guy be 1.4, the third guy be 1.41, the fourth guy be 1.414, etc., right? Then this is a monotone sequence, right? This is a monotone, strictly increasing. Well, maybe not strictly. Maybe at some point I have some zeros, right? So it's not strictly increasing. It's an increasing sequence at least. So you have an increasing sequence, and it's bounded above. It's bounded above and it's bounded below, right? What's a bound above? What's an upper bound for this sequence? 1.5, right? Or 1.42, or 1.415, right? Any of those things are upper bounds for the sequence, right? Is that clear? What we mean by an upper bound? And what's a lower bound? 1.4. Yeah. In any case, this is a bounded sequence, right? And so we see you got this sequence and it's increasing and it's bounded above, right? And what the monotone convergence theorem says is that you're guaranteed that it's going to converge to something. So this will converge to some value, to some real number. Right? So the monotone convergence theorem tells you that because this thing is bounded, there is some number that this thing will actually converge to. Okay. And that number is the square root of 2. So just one comment. As you might guess, maybe I'll ask you. What do you think happens if we're not in the real numbers? Are you guaranteed? Do you think the monotone convergence theorem is still going to work? Like if you're bounded, you have a bounded sequence, you're guaranteed that it's going to converge to something. Suppose we're not in the real numbers, we're in the rational numbers, say. Sort of giving you the answer right in front of you, right? The answer is?
Yes.
No, the answer is no. The answer is no, right? Because you look at this thing, each of these guys is a rational number, right? Each of these is a rational number. This is 1, and this is 14 over 10, this is 141 over 100, et cetera, et cetera. These are all rational numbers. It's bounded above, right? It's bounded below. But if we're in the rational numbers, doesn't converge to anything, right? Because there's a hole in the rational numbers where they'd like to converge, right? They would like to converge to root 2, but if we're back in the age of Pythagoras, there is no such number, right? So again, there's this theme that we've been hitting repeatedly. Rational numbers have a lot of holes. Okay, so in fact, the monotone convergence theorem, like many other great theorems, fails if you're just in the rational numbers. Okay. But that's not important. That's just for your curiosity. It's important if you go on in math. If you do some more stuff. Okay. So monotone convergence theorem, right, gives some meaning to infinite decimal expansions, right? If when you were a child and you wondered about, what are these infinite decimal expansions, right, other than infinite decimal expansions, right? If you think about your understanding about them, you find it sort of circular, right? An infinite decimal expansion, well, what is it? You can't really explain it in any other words except saying it's an infinite decimal expansion, right? It's like, I once asked a friend from India what a bounder was. A bounder. Does anyone know this term, bounder? And he said, it's an irreducible term. It can't be expressed in any other terms. It's like a cad, a bounder. Anyway, so he had the habit of calling us all bounders. Oh, you bunch of bounders. Okay. Okay. So, but this, now that we have the monotone convergence theorem, we say, okay, now we actually know what an infinite decimal expansion is. What it really means is that you're looking at the limit of the sequence that you get by considering the partial expressions of the expansion. Okay, so that's that. I hope that makes you feel a little bit more secure in your knowledge. I don't know. Okay. So another thing that this will help us with is understanding irrational exponents. Or irrational powers. So again, I'll ask you a question saying, what does 2 to the pi mean? Suppose I take a number and I raise it to an irrational power. Right? What does that mean? right? You should be, at this point, you should sort of be, you should have, well, I don't know. Can anyone, you might be able to guess what I'm going to say. What are we going to say? Yeah, Edie.
I don't know, but it's bounded by 2 to the 4th.
Yes.
And then on top and underneath by 2 to the 3rd.
Yes, great. So, so we're going to give it a meaning, right? We're going to give it a meaning by considering some monotonic sequence, right? And the monotonic sequence is one that you can guess, right? What sequence are we going to consider? What, you know, 2 pi is of course, you know, something like 3.14159, something, right? So what's our sequence going to be, Rachel?
Would you do A1 equals like 2 to the 3rd, and then A2 equals 2 to the 3.1?
Yeah. So we're gonna. So what we do is we say, well, this doesn't mean anything to us, right? This actually means nothing to us until you have some notion of limit of convergence of sequences. And you say, okay, well, we're going to take a sequence, 2.3, 2.31, 2.314, right? And these are all things that you can calculate, right? These are all things that do make sense to you, right? This 2 to the 3.1 is 2 to the 31 tenths. Right, that's to say you take 2 to the 31 and then take the 10th root of that. Right, that's something that you know. Right, this is also you take 2 to the 314 and then take the 100th root of that. Right, those are all things that you know. Right, those are all things that you know, and then you take the limit of those things that you know and use it to describe this thing which has no meaning to you. So 2 to the pi, and you see that this is an increasing sequence, right? And it's bounded, it's a monotonic sequence, so again, monotonic sequence, and it's bounded above by 2 to the 4th. So you've got the sequence, you have an upper bound, it's an increasing sequence, and it has an upper bound, and so it's gonna converge to something, right? And we call that thing to which it converges 2 to the pi. Okay, so that's what we mean when we talk about irrational powers. Okay, okay. So I should say that this is not really the best way to do this. Okay, if you there's another way to do that. It's more sophisticated, but in the end, this works out anyway. Okay, this turns out to be the same number as if you go the other way. So it's not wrong, but it's this is not really how one would like to do it. Okay. Just to warn you. Because we're doing it in this way, I have to give you the following information as just a fact. So if we went the other way, which is more long and complicated, then we could actually explain this fact. But we're not going to go that way. Okay. Well, instead, I'm just going to give this to you. Here it is. That irrational exponents have the same properties as rational exponents. Right? The rational exponents that you know and have some feeling for. Right. You remember for rational exponents, if you take some base to a sum of powers, then it's going to be what? What is it going to be?
A to the x times a to y.
A to x times a to y, right? Next thing I'm going to say is a to the x to the y is what?
A to the x times y.
Thank you. A to the xy, right? So these are the two basic properties of exponents, right? And so we say these properties hold for all x, y, and r. So we'll take a to be a positive number just to be safe. So that we can avoid, I'm going to take a to be positive because I don't want to take square roots of negative numbers. Okay. So these two properties hold, in fact, not just for rational powers, but for irrational powers as well, right? So if I have, 3 to the pi, right, then that's 3, it's the same thing as, well, that's not 3 to the pi, right, squared, well, that's going to be 3 to the 2 pi. 3 to the 5 quantity squared is the same thing as 3 to the 2 pi. Or if I have something like this, the square root of 2, the square root of 2 to the square root of 2 to the square root of 2, right? Then what's that? If you take 10 seconds and write down an answer. Or just think about it for 10 seconds. What's the answer? 2, right? Yeah, 2. Right, because you get the square root of 2 to the square root of 2 times the square root of 2. That's to say the square root of 2 squared, that's the same as 2. Right? Okay. So rational powers, anyway, the moral is rational powers, you can, Sarah, do you have a question? No?
No.
No? Okay. Okay, so the moral is that monotone convergence sequence gives meaning to irrational exponents, and sorry to give this to you like this, but and the irrational exponents behave like rational exponents. Okay. 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 So there's one more. One more thing that I think you've probably all seen before, but let's talk about it. So exponential function.
Can I just get a clarifying question?
Yes,
before we go on?
Yes.
For the monotone convergence theorem, it doesn't have to be bounded on both sides. It just has to have one bound.
That's a good question. That's a good question. So, well, think. If there's a bound, there's an upper bound u, and you have some increasing sequence that's bounded above. If you have an increasing sequence that's bounded above, then is it bounded below?
Not if it's strictly increasing.
Is it can somebody give me a lower bound for this? The first number is your lower bound, right? Because it's an increasing sequence, right?
Right. Okay.
Right. So yeah, you could say you only need the bound on one side. In fact, it will automatically be bounded on the other side. Yeah. So if you have and similarly, if you have a lower bound for a decreasing sequence, well, that's going to be bounded on both sides either. Also.
Okay.
Yeah. Okay. What if you have a sequence that's just convergent, not upper? It's not increasing, it's not decreasing, but it converges to some number. So it converges to some value, the limit L. Okay, so it converges to some limit L. What can you say about the boundedness if a sequence converges? So suppose if AN converges to L, what can you say about boundedness? Can you say anything about boundedness? Taylor,
Bounded?
it's bounded. Yeah, it's bounded, and you can see why. You say, well, why do you say it? Why do you say that, Taylor?
Because from the top you can see that it's not trying to go higher than the highest point and the bottom. So it's like below.
Okay. Okay, so you say here's how one explains it, using like definitions and stuff. You say, well, look, I know that I can make everybody I can find a time past which everybody is within plus or minus 1 of L. Okay, so past this point, everybody is within plus or minus 1 of L. Okay. And before that point, there's only a finite number of values. There's only a finite number of values, right? So I know that the finite guys can be bounded, right? Because there's only a finite number of them. I can always take some number larger than the biggest and smaller than the smallest, right? And then there's an infinite number of other guys, but they're all trapped, right? They're all trapped between these two things. So in fact, convergence. So if an converges, then a sub n is bounded. Okay. But the opposite isn't true. If an is bounded, does it have to converge? Well, no, right? You could have something that's bouncing back and forth, right? Like -1 to the n, like bounces back and forth. It's bounded, but doesn't converge, right? So the opposite isn't true. But in the case of monotone sequences, it is true. So monotone Rubin's theorem says that for monotone sequences, then you can actually then the opposite is true. Okay. This statement is true. This statement is true for any sequences. The opposite is true if they're monotonic. I wasn't planning to tell you that, but anyway, why not? Okay. So okay. Other questions? That will cause me to release more and more information. Yes, Joey.
Oh,
No, okay, just stretching. Okay. Right. In Chinese, there's a saying that the teacher is like a bell. If you don't hit the bell, then it won't make any noise. Why are you all giving groans of pity?
You're hitting your teacher.
You're hitting him intellectually. Right? You have to. That's okay. Hitting them intellectually is okay. That's what we're here for. Right? Right. So yeah. So hit your teachers. That's hit your teachers. Again, advice which could be easily misconstrued. Okay. Theorem. Or I'm just going to use this as a fact. If we look at the sequence 1 over 1 plus n to the n, okay, so we create the sequence 1, like, that is, for a1, it's going to be 1 plus 1 to the 1, a2 is going to be 1 plus a half squared, a3, 1 plus a third cubed, a4, 1 plus a fourth to the fourth power, etc., etc. Okay. Now this is a funny sequence. It's an interesting one. What do you think happens to it? What does it look like happens to it? Or can you say anything about what you think might happen to it? Look at it think about it for just a few seconds. Okay, anyone want to say anything? Anyone have an observation? Just make any observation about this, Samantha.
That as the n value gets increasingly large, the bottom 1 over n will go to 0.
Okay, so it looks like the thing inside the parentheses is tending towards 1. I mean, the thing inside the parentheses is tending towards 1. Okay,
Yeah.
Any other observation?
So I would think that the whole thing, just 1 plus 1 over n to the n, would go to perhaps 1 to the infinity.
That's a good guess. That's a good guess. Maybe it tends to 1, right? Because 1 to any power ought to be 1. Right.
Maybe the whole sum of the series or whatever goes to 11.
The sum. Oh, okay. Well, I'm not going to talk about the sum actually. Actually, the sum. All these values are bigger than 1. So if you're looking at a sum of them, it's going to be infinite, right? The sum of things. You're taking an infinite sum of things, each of which is greater than 1. So that'd just be infinite. But, okay. What about the exponent? Suppose you take something and you raise it to a power, and then that power becomes arbitrarily large. You have something that's bigger than 1, and you raise it to an arbitrarily large power. What happens?
It increases.
It increases, right? If I have like 1.000001 to the n, as n goes to infinity, this is going to become infinite, right? Okay. So there are two things. So another reasonable guess would be infinity, okay. Because the exponent is becoming infinitely large. Okay. In fact, there's a tug of war that goes on, right? So this guy is like, I'm trying to pull towards 1. This is going to try to pull towards infinity, and it turns out that a balance is reached at a particular number, and that number is called E. Okay. So it turns out to be close to some number, 1.7, so 2.71828, something. And this number is given a name. It's called E. The proof of this, we'll have to defer to calculus, the next class. Okay. So just to lure you onwards to the next class, it's like those old stories where they say, if you want to know what happens, you'll have to read the next chapter.
You probably won't be able to answer this because it might take too long.
Yes.
Is this what E is? Like what E? It's so like universal
Yes.
and L and weird.
This is E. This is E.
That's, like how they discovered E.
Is this how they discovered E? Is this how they discovered E? Is this how they discovered E? I don't know. That's a historical question. I don't know. I don't think so. I don't think so. Yeah.
It's so
Yeah. Yeah, I mean, as a mathematician, we have all sorts of sort of fake history in our heads. We make up a history, right? Certainly, I can make up some things, but that's not probably what happened. Yeah, in fact, probably all the stories that I told you in this class about mathematicians are not true. Rachel.
Do you think that mathematical concepts are discovered or invented?
Oh no, forget it. Discovered. Yeah. Okay. Yeah. Okay. Another theorem that again we will leave to entice you onwards to further mathematics. And e to the x, if you look at 1 plus x over n to the n as n goes to infinity, this limit turns out to be e to the x. Okay. So this is again one way of presenting e to the x. There's actually a better way. So the better way is to define the natural log using the integral, and then the exponential function as the inverse of the natural log. And this actually is the way to define irrational exponents more properly. Okay. So this is, but we can't do it because we don't have the integral. Okay. So won't be able to do it until next semester or at the end of this semester. But even though we could do it at the end of this semester, we will not do it. Okay. Okay. So there's this thing e to the x. How many of you close your eyes for a second? How many of you have not seen e to the x before? Oh, okay. Okay. Open your eyes, please. Okay. So Okay. Let me think for just a few seconds. Okay, I don't want to say too much about this function e to the x, but for those of you who haven't seen it, just think of it as it's just like if you have it's not all that different from this, right? You have to look at the function 2 to the x, right? It's just, you're taking some powers of some base. The base happens to be this particular number, okay? And for reasons that won't be clear at this point, this turns out to be the natural base. So you have these things, exponential functions based on some base. E to the x, this base e turns out to be the best base for some reason. Okay. Okay. So let me just say one thing, and that is about okay. So let me just say one thing, and that's about the growth of money in the bank. Okay, so growth of money in a bank, so-called exponential growth. Okay. So it turns out that let me say this. So it turns out that many things in nature grow in an exponential manner. Okay, so many things, for example, populations, populations of animals, of bacteria, or cells, say, they either grow or they decay in a manner that can be described, grow or decay in a manner that can be described using the exponential function. Using the exponential function. Okay.
When you say the exponential function, you mean e to the x?
I mean e to the x, yeah. So yeah, if I say the exponential function, that's what I mean. Okay. So okay. So yeah. So for example, and this is not something natural, but it's something man-made. Money in the bank. So suppose, suppose you have P dollars. Okay, this is how many dollars you have right now, and you put it in a bank, and there's this bank, and it says 5% annual interest, compounded one time per year. Compounded one time per year. Okay, so this is not a real bank. There are no banks that say this. Okay, but suppose there is such a bank. Then what this describes is a bank that after 1 year, it'll take your money and it'll multiply it by 1 plus 0.05. Okay, it'll multiply it by 1 plus 0.05, right? That's the 5%. That's the growth, the interest rate. Okay. So after 1 year, that's what it does, and then after 2 years, right, it'll do it again. 1 plus 0.05. It'll take whatever money you had after, and then multiply it again by 1.05. After 3 years, it'll do it again, et cetera, et cetera. So at the nth year, right? So at the nth year, the money you have is just going to be this. P times 1 plus 0.05 to the n. Okay. There's something else. There's something called, if they said, again, 5% annual interest, compounded monthly, let's just say 12 times per year, right? What they mean by that is that after each month, you multiply by 1 plus 0.05 divided by 12. Okay, so this is after each month, and then after 1 year, this would have happened 12 times. So, so you get this thing to the 12th. So that's after 1 year. Okay. Right. So let me sort of make a joke, right? If they did something like this, suppose they did after 1 month, they multiplied by 1.05, right? That would mean that this bank in 1 year goes through the same thing that this other bank goes through in 12 years. Everybody would go to this bank, right? That'd be crazy. This bank would fail, because they lose all their money fast. Okay. So it's not that you multiply by the annual interest rate, 12 times. It's rather that you take the annual interest rate, you divide it into 12 parts, and then do that 12 times throughout the year. Okay. So you do that 12 times throughout the year, and again at the nth year, you would have done this this many times. Okay. Any questions? Any questions? Okay. Again, suppose you have something like this: annual interest compounded daily. Okay, compounded daily. Well, what's going to be the formula for that? After 1 day, then you multiply by 0.05 over 365, right? And you do that 365 times a year. Okay. So, and at the nth year, as usual, that will have happened that many times. Okay. Okay. Suppose you have this bank, and this says 5% annual interest, compounded infinitely many times, or what's called compounded continuously. Okay. Yes, Cynthia. You want to give the answer? What's the answer?
Wouldn't it be P times E to times E to?
Don't say it yet. Don't say it. Okay. So here's what you do. You take your interest rate and you divide it by n. Okay. And you do that n times per year, right? And you let n go to infinity. You let n go to infinity. Okay? And maybe you recognize this, right? What is this? Right. I'm sorry, there should be a p here. So this is e to the 0.05, right? We just said that, right? The limit of 1 plus x over n to the n goes to e to the x, right? So this thing is going to turn into p times e to the r, to the 0.05. And that's 1 year. Okay, that's 1 year. And if we did this over t years of time, then you have a t here. Okay. Okay. So after t years of time, you would have p times e to the 0.05 t. In general, people write it like this. If you have an initial value of p and an annual interest rate of r, and t is the number of years, then the value of time t is your initial value times e to the rt. Right? So this is your value or amount, say. Amount at time t is going to be p times e to the rt. P, so your amount at time t will be your initial value times e to the rt, just like we wrote here. It will be your initial value times e to the rate times the time. And so this is the formula that probably many of you have seen before about exponential growth. Right? Things that go through exponential growth follow this formula, follow this model. Okay. Any questions about that? Any questions? Okay. Sort of standard question is, if you know the interest rate, how long until your money doubles? How long until your money doubles? Okay. Right. So you say, like, when is, the question turns into, when is P of t twice your initial value? Right? That becomes the question, right? Right. If you know the interest rate, when is your money going to double? It will double eventually, right? Because you're multiplying by 1 plus something, and it's going to double. When is it going to double? Well, you can just work it out. I guess we have 2 minutes. Take half a minute and work it out. When is P of t equal to 2p, your initial value? Your half minute is up. Who can give me an answer? Or who can tell me how? Let's work it out. What should I do? How do I figure this out? 2p equals P e r t, right? Right. So set this equal to this and solve for the time. Right? Solve for t. Okay. So what do we do? Well, we're gonna obviously, first move is to just cancel off the initial value. Right? We've got p's on both sides, so we divide by p. And that shows you that gives you some information from the beginning. It doesn't matter how much money you start off with. It doesn't depend on how much money you have. If you have $1 billion, if you have $1, it's going to take the same amount of time to double. Okay? As long as the interest rate is the same. That's actually not true in reality. Right? Like people with more money will get better interest rates. Unfortunately. Okay, so then, but in a fair world where everybody got the same interest rate, then it would take exactly the same amount of time. Okay, and then how do we get a t? How do we solve for t out of this? Natural log, right? The natural log of 2 is rt, and so the time is going to be the natural log of 2 over the interest rate. So, for example, if your interest rate were 10%, then natural log of 2 is like 0.693. Then it would take your doubling time would be about 7 years. Your doubling time, then